Welcome everyone to today's webinar on microwave mystery with mechanics. I'm Abhishek and I'm working as an application scientist for Zurich Instruments. Today we have the pleasure of welcoming Professor Remy Braaf from Université Paris-Cité and CNRS. He will talk about how to generate low phase noise microwave signals out of nano opto-electro-mechanical systems, also known as NOEMs. So before that, I would like to introduce our company, Zurich Instruments. So what we do, we make best-in-class test and measurement equipment for advanced R&D labs. How do we do it? We combine our off-the-shelf hardware components with adequate speed, high sensitivity, low noise, and high resolution, and combine it with a software framework that allows efficient workflow with very attractive UIs and functionalities that can be added over time, which also increases the value over time. Currently, we have 4 pillars in our instrumentations. For example, quantum control systems, lock-in amplifiers, boxcar averagers, and impedance analyzers. Today, however, we are going to focus on lock-in amplifiers. So in our current portfolio, we have lock-in amplifiers that are coming from 500 kilohertz to up to 8.5 gigahertz of bandwidth. And due to the FPGA nature of this instrument, we can add a lot of functionalities on them. So at the end of the day, they're just not lock-in amplifiers, but they have many such possibilities. For example, a single instrument can have an oscilloscope, a spectrum analyzer, sweeper, PID, PLLs, AWG, boxcar, and/or imaging systems. More importantly, all of these toolboxes can be run simultaneously on the instrument. With that, I would like to focus our attention on our presenter today. Professor Remy Braaf has been an associate professor at the Université Paris-Cité and CNRS since 2009. At 2021, he was selected to be the junior member of Institut Universitaire de France, while at 2022, he won the Fabrice de Grammont Prize from French Society of Optics. His research topic includes optomechanical systems with photonic crystal membranes and 3.5 semiconductor processing for nanophotonics. I believe during this talk today, he will also talk a little bit about our gigahertz lock-in amplifier and how that helped him for his measurement. Fun fact, Professor Braaf was also my PhD co-supervisor during my time at CNRS. So with that, I would like to hand over to Remy for the talk. Thank you so much.
Thank you, Abhishek, for the presentation, and thank you all of you for being there. And so, as Abhishek said, I'm going to talk about electro-optomechanical oscillators and how we can use them for a low phase noise oscillator. But also, I will try to show you that this kind of oscillator can be also used for new development that some new experiments that we do in the lab at the Center of Nanoscience and Nanotechnologies. So let's first go to kind of the basics. What is the oscillators? So the idea is that if you launch a signal, continuous signal, that with the oscillator, you can convert the energy to a periodic signal. And then this periodic signal needs to be as accurate as possible, especially for some really important application nowadays, such as modern navigation, communication, and even timing systems. And at the end, I will introduce a little bit what we could do with such a system for neuromorphic computing. But if we try to look at the first 3 applications that can be used for oscillator, we can state few challenges. Among them, of course, the stability and the precision of the periodic signals that you can create is really important in order, for example, to avoid mixing time arrival in some communication. The idea also is to work as much as possible at really high frequency, and so the gigahertz frequencies are kind of mandatory in order to avoid frequency multiplication of the frequency. And also nowadays, what we would like and what is really mandatory is to have kind of really integrated devices such that you can put it in really movable objects. And also something that is more and more useful is to have an optical carrier such that you are not, the oscillator itself is not sensitive to electromagnetic perturbations. And so all these kind of challenges you can try to summarize in one graph. Of course, it's a bit complicated, but the idea here is that you can look at the stability of your oscillator here at a specific frequency offset as function of the footprint and the compactness of the system. And everything here is at 10 gigahertz. And the idea here is to reach this area, so high stability, so low phase noise, and a small footprint. And if we look at this, we can try to investigate the state of the art in this frame. And of course, you can think about clocks, but some clocks that are quite complicated to move and to share, such that this famous Big Bang or some a tabletop experiment that, of course, don't fit to this frame. But there has been some developments with electromechanical oscillator or quartz, and some extra development with TCXO or OCXO, as well as electronic oscillator. And when you look at this, either they are quite compact, but with a relatively low phase noise, or with quartz are a little bit more bulky, but have better phase noise. But all these two solutions have a main drawback is that they are in the electrical domain, and so they are sensitive to electromagnetic perturbations. And then you have other systems based on optics or hybrid, such as electro-optic oscillators, which have a really low phase noise, but are still quite bulky, about a liter. Or you have also the atomic fountain, some possibility to make it a little bit more compact, but it's still 1 meter per 1 meter. So you see that this ideal oscillator has not been reached yet, even if the electro-optic oscillator, which is here, and if we look at the details, it's kind of some building blocks that you put together, and the main drawback, which make it really bulky, is a few kilometers of fiber that are mandatory in order to reach this high stability. So the idea to reach the ideal oscillator is to use the concept of integrated photonics and optomechanics in order to potentially reach this area of the ideal oscillator. And so I will now dive to the concept of optomechanics, where here we need 2 degrees of freedom for the moment, a photonic one and a mechanical one. So for the photonic, it's useful in order to read and probe the mechanical displacement of a mechanical resonator. And so you can see it like a Fabry-Perot cavity with one of the mirror which is able to move, and you send light at the input on resonance with the cavity formed by these two mirrors. But when the light is pushing the second mirror, the light is not anymore on resonance with the cavity, and so the mirror is coming back to its rest position. And so you have a kind of a loop like this, which imprint the mechanical displacement of this system onto the optics. And so you are able to read the mechanical displacement with optics. But in order to make it efficient, you need a really high finesse of the optical cavity. And you can, for the mechanical part, you can use a different kind of systems, which may range from the kilohertz to the gigahertz. So What you can also add to this system is kind of electronic part, which will be able to excite and as well control the mechanical displacement of this resonator. And so like this, you may expect resonant excitation of the mechanical oscillator, mechanical resonator, and also implement some feedback loop on the mechanics. And this is exactly this kind of system that we are using in the lab. And we, of course, we are not the only one. There has been many different proposals on this, either using surface acoustic waves for the electronic part, or piezoelectric actuation, or even planar superconducting resonator on silicon. But all this transition from microwave to optical domain have been used and developed for quantum application. And so in our case, we are trying to implement some other application as an oscillator, as a low phase noise oscillator. And so the idea in our case is to really use this microwave photonics in order to generate high purity radio frequency signal with a photonic crystal cavity. Just aside, we are also using photonic crystal for nonlinear dynamics, but I won't go to the details of this. I will focus on this part and explain you a little bit the image that we are seeing here. So this image is the same. Here, what we use as a photonic part, we are using a photonic crystal cavity in order to confine on a sub-wavelength range the light at 1550 nanometer. And here you see that the mode profile of the electromagnetic modes at 1550 nanometer. And on the mechanics, we are using a phononic crystal, which is working in the gigahertz, in order to confine mechanical modes. And you can see here the mechanical profile, so the displacement profile of the mode that we are using. And this mode is, depending on the geometry, around 3 to 4 gigahertz. And we have, because the system are coupled and they are at the same place inside the photonic crystal or the optomechanical crystal, we have a strong coupling between the optics and the mechanics. And so we have, thanks to a photoelastic effect, optomechanical coupling. And here you see some zoom image of our system. Here is more the optics that's in blue, and there is the mechanics more or less at the same time, at the same place. And here, how it works, we have a heterogeneously integrated gallium phosphide membrane on top of this silicon photonic waveguides. And so what we had here, we had the electronic part, which is thanks to a piezoelectric effect, we can have electromechanical coupling between these electrodes in yellow here and the mechanical part at the center of the system. And here you can see that the line for the electrical field between the two electrodes on the side and the photonic crystal cavity in the middle. So with this, we have a kind of a strong control of the mechanics, either through the electronics or through the optical part. And so, of course, here, because we are integrated on a silicon circuitry, we have a strong interaction on a photonic integrated circuit. So the idea is to use this platform in order to first demonstrate oscillator and also to use this electrode in order to implement this feedback loop that you can see with this square, this rectangle B. So like this, we have ultimate optical confinement and acoustic confinement, either the first one at the telecom wavelength and on the gigahertz range, which is directly imprinted on the optical carrier, and we have a pure gigahertz signal. And so this is integrated, we imagine to have an integrated microwave photonic oscillator at the nanoscale. So if we go a little bit more in the details, and first we look at the optical carrier that of the photonic crystal part of the system. We launch a laser at close to the resonance of the system, and we look with power meter at room temperature and ambient pressure. We look at the power that we collect at the end. And by sweeping the laser around the photonic crystal across the resonance, we have this kind of dip, and we can extract photonic crystal optical quality factor of about 10 to the 5. And with this, we can try to measure the mechanical mode of this structure. And we have a direct modulation at the gigahertz frequency. And thanks to a parametric amplification, we see line width narrowing and an amplitude increase of our RF signal. So in blue, it's when we are close, well, not really on resonance, not yet. And when we change the wavelength of the laser, we see a shift in frequency, but more importantly, an increase in amplitude of the signal that we can record. And of course, we see also line width narrowing. And this is this part that we are trying to measure in order to characterize correctly and completely our system. So if we do so by just mainly looking at the phase noise performance of our system when we have an open loop here, so we have not yet implemented the feedback, we see that depending on the wavelength, so the same wavelength I showed you before, we see that the phase noise is decreasing up to a point where we reach something like minus 80 dBc per hertz at 100 kilohertz offset from the frequency carrier. And it means that the line width of our system is below 1 kilohertz, and we have a frequency tunability around 6 megahertz for this kind of structure. But now what we want to do, we want to implement a feedback loop. So we need to look and to use these two electrodes in yellow I was talking about before. And here we simply use for the moment, in order to characterize the system, a signal generator and electrical spectrum analyzer. In order to see the response. And what we do, we sweep the actuation frequency, so the signal generator frequency here in the diagonal, and each line is one recording with the electrical spectrum analyzer. And what we see three regions. The first one here with the two systems are not locked. And so we see some beatings between the drive and the mechanical resonance here. And at one point, we have a locking range where we have only a kind of a combination of the the drive and the mechanical mode are locked. And then when we increase again the frequency of the actuation, we come back to a non-lock state, and we see the beating again between the two frequencies. And here is on the bottom is two spectrum at two slightly different frequency, and we see in orange when it's locked that we have only a really sharp peak when the mechanics is locked with the drive. And this is with this that we will try to do the feedback loop of our system. This before, at the beginning, we were using two equipment, so the signal generator and the electrical spectrum analyzer. And now we replace this by this SHFLI that we can do with only one equipment, exactly the same measurements. So for the feedback loop, what we do is we use here these electrodes once again with this 210 meter of fiber spool in order to have a sufficient delay in order to improve the performances of our system, and some filtering and amplification of the RF signal. And then we inject this directly to the electrodes in order to improve the performances of the final system. And so here we use this 210 meter of fiber, which gives you around 700 nanoseconds of delay. And this excitation is now integrated such that we can get rid of any electro-optic modulator that we may have had on the path of light, of the laser. So if we do so, you have this kind of performances. So in blue, it's when the loop is open. So this is more or less the same performances I showed you just before. We have somehow minus 80 dBc per hertz. And when we put this optoelectronic feedback loop on, we reduce at this given frequency, we reduce the phase noise by something like almost 30 dBc per hertz over a large range of offset frequency. And somehow, if you are not so familiar with this kind of metrics, you can look at the line width. When it's open loop, the line width of our system is around 300 hertz, but we go sub-hertz when we have implemented this feedback loop. So we demonstrate here integrated optomechanical or electro-optomechanical oscillator with a relatively low phase noise. And so now we can try to compare this with other performances of the other optoelectronic or optomechanical system. So here, currently, we are not the measurement I've just shown you are here around this point. Because again, for the footprint, we need to use 200 meters of fiber, and the phase noise here, when we report it at 10 gigahertz, we need to have a conversion factor that brings us up to minus 80 dBc per hertz. But since then, we have first reduced the phase noise of our system, so we are going down in this direction. But we have also some other developments that we try to put in place, such that improving to reach higher mechanical quality factor, which is something that we succeed recently to have a few order of magnitude higher, and also try to have higher optical input power. And for the delay, in order to reduce the footprint of our system, we are thinking to work with on-chip delay line using phonons instead of photons. And of course, trying to work on the packaging and from the optical and the RF part in order to, again, reduce the footprint and the efficiency of our system. And so at the beginning, I talk about okay, oscillators, what we can do, which kind of application, but we can also do other things with it. And I was talking about neuromorphic stuff. And this is the second part of my presentation, where we can try to use this kind of oscillator as artificial neurons. And so here, the basic function of neurons and it's to give all or none response to a dynamical perturbation. So of course, there have been several implementation already of this kind of artificial neurons with electronic devices, but also with optical device with laser, but this is kind of a tabletop experiments once again, or with integrated optical cavity and purely optical cavities, and also with levitated particles where the light is probing the mechanical displacement of the system, but there is no back action, so there is no action of the mechanics on the optics that we can do with optomechanical system I have just shown you previously. So here, if you want to dive a little bit more in the concept of artificial neurons, one of the implementation, there is not the only one, but the one that we have developed with this optomechanical system is to use a self-sustained oscillator, because this is what we have in hand for the moment, and to implement a weak driving force in order to take advantage of this kind of Adler equation, where you have the phase evolution is equal to the detuning between the oscillator and the drive, plus a small modulation and a sinusoidal evolution of the phase. And you can, in this case, with this kind of equation, you can create locking regions that I have already discussed previously. And you see that we have already this kind of response for our system. But what I would like to do is to take advantage of this, but to shift a little bit the representation that we can have, because with this locking region, we can investigate, we can put it in a slightly different way with create 2 points, unstable and a stable point. And this stable point is where our system is when you are locked, and the unstable point is when you are unlocked. And you see that there is, in the phase space, you have a phase difference between the two. And this is really important for the following, because it's this phase difference that we need to work with and to overcome in order to demonstrate artificial neuron. So the idea is to add a perturbation, phi Hertz, that should be either smaller or bigger than this phase difference between the stable and the unstable point. So if the perturbation is smaller than the difference between the two states, even if the perturbation is happening, the system is directly coming back to its stable point. So there is no excitation. But if you overcome this difference, so if the perturbation is larger than the difference of phase between the two, these two states, you have an excitation, and it has to be 2 pi phase shift. So the system cannot come back with like the result following the red arrow, but has to go along the full circle in order to come back to the stable point. And so this is with this picture in mind that we need to think about the system, about our possible artificial neuron. And so what we do with exactly the same system I have discussed before, we have a weak driving force that is going to come from the drive of the locking region, of the locking, which has to be close to the mechanical resonance, so close to this 3.3 gigahertz. So we need this SHFLI, and at the same time, we will record the response of our system in order to understand how the system behaves to a specific perturbation that in this case will be in the optical domain. And so this is here we use the electro-optic modulator, and we have AWG, external AWG, in order to control the size of the pulse of the perturbation that we will input into the optical domain. So for the weak driving force, it's something that I have already shown you. So we can control the mechanics through the electronics, through the electrodes that are on both sides of our system. So again, it's exactly the same figures that I've shown you before. But more interestingly, it's something a little bit different. It's the perturbation, which is on the optical domain. And with the optics, we can also control the mechanics. So here, what we see is the frequency of our system, so around 3 gigahertz, as function of the power that we input in the structure. And what we see is that there is a drift of the mechanics as function of the power. And this drift in frequency had induced a shift of the phase of the oscillator. And so we can control this phase difference. And so we create a phase perturbation in our system by just jumping, or increasing suddenly the power between this P0 to another value. So this is what we are doing. And when we are close to the locking region, so close to the edge of the locking region, so here it's only a few kilohertz, and that the perturbation, the amplitude of the perturbation is really low, so somehow 10% of the threshold of the P0 that I was talking about. Here is the time trace of the amplitude that we can record. And thanks to the locking amplifier, we are able to have the phase portrait, the IQ portrait, and we see that the system is staying around a position which is stable point, the stable point that I was talking before. But now, if we increase the power of the perturbation and we go above threshold, here it's 80%, we see that we have a clear difference. So here, at the really beginning, the sharp peak is our perturbation, and we have a specific response few microseconds later. And if we look now at the phase portrait, we see that we have a clear jump from this point, which was the stable point, to another part of the circle of the phase portrait, and the system is coming back following the circle of the phase portrait in this direction. And this, you see, is the first one perturbation, and at the second perturbation, we have exactly or really close to the same perturbation, or to the same response. And so here it's only two different perturbations, but of course we did this over 5,000 perturbations, and we can do in this case a statistic, and we look at the median of this all or none response. And when we are below the threshold, of course, we are not able to read any response. So we are in this case here, and suddenly we have an abrupt change, and we see kind of almost always the same response. And this we can, as I said, we did here an example for 6 kilohertz. So we are close to the edge of the locking region. But if we change the position in the locking region, so if we go deeper in the locking region, of course, we need to increase the amplitude of the perturbation in order to reach probability of spike excitation probability close to 100%. So in yellow, it's when it's 6 kilohertz. So the result I've shown you before. And when the brown is 2 kilohertz more inside, and we have a threshold which is a little bit higher. And when we are at 10 kilohertz, we barely reach 40% of probability. So with this, I think I've shown you that we have on-chip electro-optomechanical crystal, and with this kind of device, we can do two different things. A low phase noise oscillator that we can improve its even further its properties and its performances, and also we can try to do some artificial neurons with this kind of systems. With this, thank you for your attention.